Okay, you guys can, if I can get this situated here, you guys can turn in your books to page 334. We're going to start and we're going to talk about blood over the next probably week and a half. I had several people ask about the chapter packets, and those will pretty well be due. I don't have my weekly paper in front of me here. Those will be due, let's see. I had the wrong date on y'all's weekly paper, didn't I? We'll probably Wednesday we'll plan on having this test, the test about blood. So you can kind of plan on that. What we'll do is Monday I'll do the last little section of lecture. I'll do that for a video Monday. And then on Tuesday, we'll do your chapter packets will be due on Tuesday. We'll grade those in class, answer any other questions. And then we will go on Wednesday, we'll take a test, and we'll go ahead and get started on the heart. So we'll probably do, now they've done a week and a half of blood, we'll probably do another week and a half of the heart and be done with that so we can move on. And yeah, we are really closing it in. Now, we just have, we have 2 months of class left. So a lot going on, a lot to do, and we'll get started. So blood, this is a really, I think, an interesting chapter. I think sometimes it's a little easier because, it's something that's tangible. It's kind of I don't know, like people take your blood for whatever reason, and so this kind of gives you an idea of why they're doing that and what they're looking for. So you guys can follow along in your PowerPoint. Function, these are some of the things that we'll look at: the function, the formed elements, we'll talk about what those are, the properties, and then we'll look at plasma itself. Okay, so the function and composition of blood, there's actually on page 335, it talks about the different functions of blood. There's a table there. Looks like this, top of 335. So that's a good place to really get some good information. So one function of the blood is that it transports. Okay, that's pretty well kind of the main purpose. I would say main purpose, they're all important and we all need them for life. But when you think about the blood and it kind of its purpose is to transport oxygen, which is what all of our cells need. So it transports oxygen, carbon dioxide, transports waste products so that our kidneys can get rid of it. Transports hormones. That's how hormones, we just talked about hormones. They leave one area and have their target organ, so they travel through the bloodstream till they reach their target organ. Enzymes, we know those speed up, act as catalysts and speed up chemical reactions. Carry some nutrients like your glucose, fats, your proteins, all of those things that we need in order to function. Of course, it transports blood cells. Specifically, blood cells are the ones that carry oxygen, but also you have your white blood cells, that work they have an immune response. They function to protect you. Then the plasma proteins, which we are going to talk about in a little bit, they have their own kind of jobs. Another function, main function of the blood is to regulate, is in different parts of regulation, so homeostasis. So one is body temperature. Okay, you know how we talked about body temperature, our hypothalamus is kind of the go-between as far as that goes. It's kind of acts as our thermostat. But if you've ever noticed, like those blood vessels, when you're really hot, they dilate so that blood can be close to the skin, which is cooled by the outside of the body, or sweat, along the skin too. Or they constrict and kind of go deeper inside the body to keep their warmth. The acid-base balance. So we know, you guys remember from chapter 2, I think it was, the pH of blood, 7.35 to 7.45. And so it's really important that blood has the capability to stay within that frame, that range, that safe pH range, and to stay in that range and function, you know, I mean, it has to be there in order for us to function. Fluid and electrolyte balance. Of course, we know we have to have a certain amount of sodium and potassium and magnesium, all of those things for our nerve cells to function, for our bodies to function the way that they need to. So blood helps to regulate that. And then lastly, blood protects. So white blood cells protect our body against foreign microorganisms, old cells that don't function anymore. Antibodies detect foreign material, so antibodies are created. And then, of course, clotting factors. So when we're injured, we don't just, you know, bleed to death every time we get a little injury. Okay, it clots. It functions so that we can, you know, we can sustain injury. Whenever we think about the composition of blood, we kind of have two basic parts. We have the plasma, and then we have the formed elements. Okay, the plasma is like the liquid part of the blood, if you will. Okay, the plasma is a clear fluid. We'll talk about it more in detail in just a little bit, but it's kind of a clear, yellowy fluid, and versus the formed elements, which are your solid things, your white blood cells, your red blood cells, your platelets. Those are kind of solid things in the bloodstream. I'm going to leave a couple of tubes, like lab tubing out. I want to show you guys kind of what that looks like. We'll go from there in a minute. So definitely formed elements or solid elements. I think it called them the solid. In the book it said solid. Oh, I thought it was somewhere else. But anyways, called them solid something. Maybe it said solid elements. But anyways, formed elements. And then whenever somebody takes your blood, there's a few different things that they can do. Let me grab my tubes, and I'll show you.
Brenna Walker, report to the field house now. Brenna Walker, they're waiting on you.
Okay. So there's different types of tubing. I'm going to leave these out so you guys can look at them and see some of the differences. Okay, this tube, and I know you guys can't see it because whatever, but anyways, it's the one that's like red and black kind of striped whenever you're looking at these. Sometimes they call these a tiger top. That's usually what they say, I need a tiger top. What that means, this one actually has gel in the bottom of it, and you guys will be able to see that. And what happens is whenever you put this in the centrifuge, okay, the thing that spins blood around, this gel actually moves up. And so if you go over to 336. Okay, this one, they have a purple top on here, but you can also do some different things. But see how on page 336 you have the plasma at the top, and then you have the buffy coats kind of right there in the middle, and then you have red blood cells on the bottom. Whenever it spins in the centrifuge, that's what happens. This one actually has gel between the plasma and the red blood cells. So this gel, actually, whenever you see it, it's kind of crazy, I guess because of its density. It actually will be between the plasma and the red blood cells, and so you'll see, you know, they're separated so they can check what they need to check with this. Now, I don't have any red. Oh yeah, I do. Okay, there's a plain red top in here, and I'll leave this one out too. This is a Vacutainer, what they get blood in, and there's reasons that they have different colors. And red top doesn't have any gel in it. They'll still spin it down, and it'll look kind of like this one does, but it doesn't have any kind of additive in it, any kind of preservative. The red top doesn't have anything else in it. Whenever you put blood in there, it stays in there, and it will clot pretty quickly, usually in a red top. These that have blue tops on them, if you guys look at them, some of my blue tops that are in here are really old, so they don't have the fluid in them, but most of them have a little bit of fluid in them, and you have to fill these up to a certain, they usually have the right amount of suction already in them, but you have to fill them up to a certain place. And what they look at for these blue tops, this is how they measure your clotting, like it's called PT and INR, and they check that with the blue top because these have that in them, and it keeps them from clotting like they would in a red top, the liquid that's in there. And that's why they use it. They actually are able to see kind of how long it would take your blood to clot, and if your blood is clotting too fast or not clotting fast enough. And then the last one that you'll see in here is a purple top. And I'm not sure what the additive is in here for. I know that it will not, or it shouldn't clot up on you like it would in another one. But usually those purple tops, you use them to measure like a blood count, hemoglobin, hematocrit, those kind of labs. Usually a red or a tiger top you can really measure your plasma. You can measure, well, not just measure the plasma, but what's in the plasma. So your electrolytes, potassium, sodium, those are all things that you would check with one of these. So that's why whenever they take blood from you, they take them in different colored tubes, because each tube is for a specific reason. There's different labs they can get from different tubes because they have different additives in them or have different purposes. So anyway, it's just a side note. I think it's worth talking about. So excuse me. The last solid portion of the blood are the platelets. I may have said that earlier, but platelets, their purpose is to clot. I mean, to keep your blood keep you from bleeding out all the time. All right. Okay, the physical properties of blood. So what it looks like, tastes like, etc. Volume of blood. For the most part, most people have 4 to 5 liters of blood at any given time. Now, this does depend on the size of the person, muscle mass. Pregnancy almost doubles the amount of blood supply in the body. Muscle mass, like I said, size, activity level, though all those things can change this somewhat. But total blood is usually about 8% of your total body weight. It's just blood itself. It tastes salty. That's because your blood actually has a sodium chloride level. It's 0.9%. If you guys have ever looked at a bag of normal saline, which we probably did whenever we talked about osmosis and things like that, normal saline is we call that an isotonic fluid. If you remember, isotonic is same. So it's 0.9% sodium chloride. So that's how we know. That's why it's isotonic, because it has the same percentage of that as in our bloodstream. Of course, the pH, you guys know, 7.35 to 7.45. The color, bright red. Oxygenated blood is typically bright red. Dull if it's already gone through and kind of been used up. I don't want to say, I know the PowerPoint says artery and vein, but there is one exception to that. More than one exception actually in a fetus, but for us, one exception to that is the pulmonary artery and the pulmonary vein. The pulmonary artery is actually deoxygenated, and the pulmonary vein is oxygenated because it heads back toward the heart. So that's why I don't like to say bright red is arteries and dull red is veins. That's not necessarily always the case. The blood is very viscous, so it's really thick, and some things sometimes it's thicker than others. One of the labs that we look at to look at blood volume is called a hematocrit. Hematocrit, hematocrit. And this gives you the percentage of red blood cells in comparison to your total blood volume. Okay, so that's a hematocrit, total percentage of red blood cells in comparison to total blood volume. Typically for women, it's about 40%. It's what the book said. For men, 45%. So somewhere in that range is your normal number of red blood cells per total volume of blood. Now, sometimes our hematocrit, okay, is increased, which means we have an increased number of red blood cells. If we're really dehydrated, and if you think about it, our hematocrit is not always necessarily about a number, because it's a percentage of your total blood volume. Sometimes hematocrit can go up when we're dehydrated, just for the fact that our ratio of red blood cells to, other blood fluid, like your plasma, for example, is off. That ratio is off. It's going to make your hematocrit go really high. Another reason you might have a higher hematocrit than normal is if you live at high altitudes. The purpose for that is that it's harder for our blood cells to carry oxygen, and so our body automatically increases the amount of red blood cells in our body so that we can increase the amount of oxygen that can be carried at one time. Make sure I covered everything on here. But yes, so that's hematocrit. Okay, it's just kind of like your percentage of your red blood cells in comparison to your blood volume. Okay, plasma. Here's that picture of the, whoopsie. Go ahead there. Here's a picture of the tubing. You can see how it separates there. Okay, plasma is the liquid portion of the blood. Okay, it's not the blood cells, not white blood cells, not red blood cells, not your platelets, but pretty much everything else. It's 90% water. It's just water. It's usually pale yellow. So whenever you look at it in a tube like this, it's going to be kind of pale, yellowy looking. About 8% of it is plasma proteins. And then 2% of it is your electrolytes, nutrients, respiratory gases, so some like free-floating oxygen, carbon dioxide, bicarb, and so forth, hormones, waste products. You also find buffers in there. Buffers help to manage your pH in your bloodstream. And then bicarb is another one, and it carries carbon dioxide. Now notice in here you have one more area that you'll see in the lab, and that is the buffy coat, but it is still the part of the formed elements. It's white blood cells and platelets. Okay, so those still count as formed elements, but that's the buffy coat. It would actually be in the middle between the plasma and the red blood cells. Look on this next table. Oh, yeah, this table. This one kind of gives you an idea of the blood cells in relation to each other, how many. So look, this is per cubic millimeter. Okay, we're talking like the size of, a pin dot on your paper. 4 to 6 million red blood cells. Okay, white blood cells, 4 to 11,000 is the normal. And then, of course, platelets are 150,000 to 440,000. The red blood cells by far outnumber everything else. Look on page 338 with me real quick. There is a chart at the top of 338. Talks about the different plasma proteins. Let's read that for a second. All right, so we have albumin. Look, its origin is in the liver. And look at its function. Regulates osmotic pressure of blood and blood volume. So that means it's going to help regulate water levels in our blood. Transports lipids, so fats, hormones, and other solutes. That's the purpose of albumin. Globulin, we've got different types. For the most part, come from the liver. Blood clot formation, the alpha globulin transports lipids, fat-soluble vitamins. The beta globulin transports lipids and fat-soluble vitamins, and then the gamma actually help fight infection. And then the last one on here, the last protein on here is fibrinogen, and this helps in clot formation, which we'll actually talk about in just a little bit. Excuse me. All right. Keep on moving. All right, manufacturing blood cells or hematopoiesis. Now, we have talked about this word before when we talked about the skeletal system. And we talked about this word hematopoiesis. Remember, hemato is blood. So when you hear hemato, think blood, whatever it is that you're hearing, okay? this is the process of making new blood cells, producing blood cells. Stem cells within the bone marrow are what makes blood cells. Some of our lymphatic organs also make white blood cells, okay, like the spleen, thymus, etc. But for the most part, we get most of our blood cells from our stem cells. Now, these the red bone marrow is where we find this. Now, red bone marrow is, you'll see some red bone marrow in the ends of your long bones, but also you see a lot of red bone marrow in your flat bones, ribs, hips, and so forth. Let's see what it said. Yeah, vertebrae, ribs, hips, sternum, and skull. Sternum is the one I couldn't think of. Sternum. So these produce stem cells and blood cells. Okay, lymphatic tissue is the other place, but for the most part, we see them in the red bone marrow. There's a picture on page 339 if you guys are still in your book and you can kind of see, shows you at the top of that page kind of where you find that red bone marrow. All right, red blood cells or erythrocytes. Most of you guys probably know that word. Erythro is red, cyte is cell. So red cell is literally the meaning of that. Their shape and size, they are usually disc-shaped. They kind of look like UFOs, if you will, or like a donut, but the donut hasn't had the hole punched out. So you'll see them that way. They don't have a nucleus. Mature red blood cells, at least, don't have a nucleus. They actually shed their nucleus so that they can pack in more hemoglobin that carries oxygen. So they get rid of pretty much all of their organelles within the cell. I think we talked about this when we did the cell chapter. They pretty much get rid of all of their organelles except for what they have to survive, and then they just keep hemoglobin and they just pack themselves with oxygen. A couple things about them being disc-shaped that are important. One is that it increases surface area. The more surface area, the more hemoglobin that can stay on their surface, the more oxygen molecules that can be carried. And the disc shape also helps to increase their flexibility, so they can twist and move and kind of like an inner tube, I guess, maybe, around, because some of the capillaries are so small that even the red blood cells have to like squeeze through them just one at a time. And then the third thing is that because the way that they're shaped and because they lose their nucleus, this actually really limits their lifespan. Hemoglobin is actually a protein that stays on the outside of the blood cell that binds with oxygen so that it can be carried. It has two parts. It has what's called heme. Okay, this is what binds to oxygen, and then globin, which actually binds to carbon dioxide. One red blood cell, okay, has about 250 million hemoglobin on it. So one red blood cell can have 250 million hemoglobin. Now each hemoglobin molecule has 4 heme binding sites that can hold an oxygen molecule. So what that means is that one red blood cell, remember you have 4 to 5 million, okay? One red blood cell can actually hold about 1 billion oxygen molecules. It's pretty intense. It's pretty crazy, actually. Anyway, so each hemoglobin molecule, again, 4 binding sites for oxygen, and there's about 250 million hemoglobin molecules on one red blood cell. I do want you guys, at the back of the classroom, if you guys will look, there's a poster back there that says Visualizing Blood, and it has really good pictures on it about the different types of cells that are in our blood, really good pictures. I do want you guys to look at it before you leave today, but even right now, you guys can look back there and you can see the red blood cell really well. Kind of an interesting picture. Now, normally, you guys, we've talked about this before, I think, but if you guys have ever gone to donate blood, they always look for your iron level, okay? And so they check your iron level is what they call it, quote, iron level. And it's usually, you know, somewhere around the 12 mark. I think they require it to be 12.5 maybe for you to donate blood. Well, what they're actually checking is your hemoglobin levels. So normal hemoglobin levels the range is like between 12 and 18. And the reason that they call this your iron level, or that you hear it called your iron level, is because hemoglobin has to have iron in order to function, in order to be produced. It has to have iron. So if you don't have enough iron, you're not going to make enough hemoglobin, which carries oxygen. And so the reason that they limit that, especially for donating blood, is that if your blood's not carrying enough oxygen anyway, are you really going to be able to make up the amount of oxygen if they take that blood away? Okay, erythropoiesis. This is specifically the process of making red blood cells. Okay, red. We'll go from there. Now, a couple things, few things that you need in order for erythropoiesis to happen. You have to have iron, like I said, because we've got to have those hemoglobin molecules. Folic acid is another one. Vitamin B12 is another thing that you have to have, and then protein. You'll notice, you guys have looked maybe we've talked about it in some other classes, but anemia, iron deficiency anemia, there's folic acid anemia, and there's also a vitamin B12 anemia. It's called pernicious anemia. So you'll see people with these types of anemia, and this explains why those are related, because we have to have some of those items in order for erythropoiesis to occur. Now, how this gets kick-started into happening is erythropoiesis. So our body, our kidneys are constantly filtering our blood. Okay, so when our kidneys, the oxygen levels, oxygen that our blood carrying goes down. So they pick up on this, that we're not carrying enough oxygen with our blood. Could be for any number of reasons. Could be that we have an iron deficiency anemia. Okay, it could be that we're not making enough iron. It could be that we're decreased in red blood cells as a whole. Could be any number of reasons. But so our kidneys recognize that we're either low on red blood cells, or our body recognizes that we're low on oxygen carrying capacity. And when that happens, the kidneys secrete a hormone called erythropoietin. Erythropoietin. Now this hormone actually stimulates erythropoiesis in the bone marrow. So the kidneys are actually the kind of initiate this process of like remaking red blood cells. Okay, so at that point, this erythropoietin stimulates the stem cell production in our blood, in our bone marrow, to produce red blood cells. Now, then what happens is our oxygen levels go back up. Okay, so our blood gets to where it's carrying enough oxygen. Our kidneys catch hold of that, and then our kidneys decrease the amount of erythropoietin that they're secreting, which in turn decreases our bone marrow and not decreases our bone marrow, but slows down the erythropoiesis process of making those cells in our bone marrow. So it's just a constant, just a constant, it's homeostasis, it's just constantly working. You can see a really good picture of that on page 340 at the bottom. Low oxygen in blood, kidney secretes, stimulates red bone marrow, which increases red blood cell production, which results in an increase in blood, which is going to decrease in hormone. Look at this, conditions that cause low oxygen levels in the blood. It's in the middle of that picture on page 340. Chronic obstructive lung disease, okay, so that's going to decrease the amount of oxygen in our blood, and then an increased oxygen intake by our tissues. Like, for example, somebody who exercises a lot, they're probably going to have more, like a higher hematocrit than somebody who doesn't exercise a lot, because their body is using up oxygen faster. They had to make extra red blood cells to be able to carry the oxygen that they need. Now, recycling blood cells. Okay, so like I said, the lifespan of red blood cells is relatively short. It's about 120 days. It says on here, so what, 3 or 4 months. And what happens that they just, in light of the fact that they have no nucleus, they get kind of run pretty ragged through our bloodstream. they, you know, they're like workhorses. Red blood cells are. They're constantly, I mean, they carry as much oxygen as they can possibly hold. They get rid of everything else so that they can carry oxygen. That's all they do, you know, for the most part. And so they do. They die after that 3 or 4 months. In light of that, the phagocytosis occurs. If you remember phagocytosis, that's where you have a white blood cell that actually kind of almost like eats another cell or a foreign body. Okay, so that is what occurs. Macrophages in the liver and the spleen actually eat old red blood cells and get rid of them. Pretty crazy that our body takes care of it that way. Hemolysis is kind of like the end result of the end of that lifestyle. Hemolysis, hemo is blood, lysis is like destroy. So literally they just kind of like rupture open. And in light of that, our blood kind of scavenges for things that it can use. So hemoglobin molecules and so forth either can either get reused or those get stored and they undergo phagocytosis as well. All right, white blood cells or leukocytes. Leuko means white, cyte means cell. So let's look at some of these. We're going to kind of go through these slides in kind of a strange. They kind of repeat. So, anyways, look over at page 342. Now, our white blood cells, remember, are cells that fight foreign bodies, any kind of infection. They fight things away. They actually have this unusual ability to move in and out of our blood vessels. So white blood cells, any given time when you check a white blood cell count, okay, it's not necessarily, you know, they're checking white blood cells in the bloodstream, but your white blood cells are constantly moving in and out of the bloodstream. They come into your blood, get moved around, they go back out to your tissues to fight off invaders. So that process is called diapedesis. D-I-A-P-E-D-I-S-I-S. Dia means complete usually. Ped usually means feet. So anyway, process of completely moving. I don't know. I'm not exactly sure on the original meaning, but anyway, so just a way to think of it. But they do. They're able to move. If you want to think of ped as a foot, it's kind of able to move in and out. That's diapedesis. Typical white blood cell count in the bloodstream is 4,000 to 11,000 white blood cells per cubic millimeter. So a lot, but not nearly as many as red blood cells, like we said earlier. Okay, and there's 5 basic types of white blood cells. We have neutrophils, eosinophils, basophils, lymphocytes, and monocytes. And let's look at some of the difference in these. There's actually a picture of these on 344 if you want to go to that picture. It's a whole big table. You guys can go to that, and it kind of gives the same information. Okay, one of the things that they do in looking at white blood cells is they take your white blood cells, put them on a slide, and then they use what's called Wright's stain. And this stain will darken the nucleus. Okay, it also darkens granules. So we have 2 types of white blood, 2 like main groups, we'll say, of white blood cells. We have granulocytes and agranulocytes. And remember, A at the beginning of a word means not. So granulocyte means they're like grainy cells. Okay, they have granules in them. Agranulocytes would be not grainy cells. Is the literal meaning for that. So granulocytes, when you look at them, kind of like you see these on here, and you can see them on 344, they have these little dots in them, in their cytoplasm. Okay, hopefully you guys can all see that. Those are the granulocytes. Okay, so the first one on here is neutrophils. And look how they stain differently. This is how you can tell what they are under a microscope, and how they stain differently according to how you use the stain and so forth. So by far the most of our white blood cells are neutrophils. They perform phagocytosis. They kill bacteria, fungi, anything that's, you know, a foreign invader type of thing. They are our first responders. So when we first get exposed to something, the neutrophils are the ones that actually respond the quickest and the first. If you have a decrease in neutrophil count, you are severely immunosuppressed. And this is one of the things I always say they want their ANC. Is sometimes you'll hear that term. That's absolute neutrophil count. Excuse me. And like when they do a stem cell transplant and things like that, they usually want their ANC to be 0. They actually kill off all of their neutrophils so they can replace their stem cells and their body can make new cells. Those are neutrophils. Eosinophils, these look a little bit different as you can see on here. They destroy worms like parasitic worms, and then allergic responses is another thing that you hear about these. Basophils releases histamine that intensify the inflammatory process, like your allergic reaction type of response. It says liberates the anticoagulant heparin. Heparin is a anticoagulant, so it's something that can be released in your blood that makes your blood not clot. These are really active, like I said, in allergic reactions. So you're allergic to peanuts or something like that, these are going to start acting up. Okay, agranulocytes are these next two. And if you'll notice, their cytoplasm is really clear. They don't have all those little granules in them. So agranulocytes. First we have lymphocytes. These already make up your T cells and your B cells. And these are kind of like specific white blood cells. They have targets. So B cells produce antibodies, and if you'll remember, antibodies are elements in our body that can fight off specific diseases. Okay, so I've had chicken pox. I have antibodies for chicken pox. So if I get exposed to chicken pox again, my antibodies are ready to go. They're ready to attack it. Now T cells fight cancerous tumors and viruses, so they become really important as well. Monocytes. These are actually our largest white blood cells. They're pretty big. Look at the size. Well, the size on here doesn't necessarily look like that, but they are largest white blood cells usually. And it says these perform phagocytosis. They live longer than neutrophils, morph into macrophage that then removes dead cell debris and attacks microorganisms. So these actually change into macrophages, which engulf old dead cells, other things our body doesn't use, attacks microorganisms and so forth. So as they stay in the bloodstream 1 to 3 days, and then they go to the tissues and act, like I said, like a macrophage. All right. Platelets. Oopsie. Or thrombocytes. Thrombo means clot. Okay, so cyte is cell. So this literally means clotting cell, thrombocytes. Erythrocytes, red cell. Leukocyte, white cell. Thrombocyte, clotting cell. I almost said dead cell. Clotting cell. Okay, hemostasis is the process of blood clotting. I just always remember blood stays. I think stasis stays, like it stays, you know, in one spot or whatever. Now, don't get this confused with homeostasis. Hemostasis. Hemo is blood. Okay, hemo, blood. So this is how our body actually stops bleeding. Couple things about platelets. One, they are, before I go too far, platelets are not whole cells like red blood cells. They're actually cell fragments. They start out as megakaryocytes that are broken up into little pieces, and then that's how they function. So they're actually much smaller than regular, like your white blood cells. They don't have a nucleus. And old platelets are removed by phagocytosis in the spleen and the liver, so they get removed as well. One other thing to make note is that on a normal day, if you don't have an injured blood vessel, the inside of your blood vessels are really pretty like, they don't, platelets won't normally adhere to it. They have this fluid on them that kind of makes them slippery, makes platelets slide off of them so that they won't stick to them and start making a clot when it doesn't need to. That is called prostacyclin. It's on page 345 at the very beginning of that first paragraph there. So it's kind of like it's called it like a platelet repellent. So normally our platelets will not stick inside our bloodstream unless there's something else that has come up and caused it to do so. Now, the steps of hemostasis, and these are in your book on page 345, so you guys can look on there as well. So stage 1, let's say you're playing baseball and you get a baseball, it's thrown, and it hits you in the leg and causes a big bruise, okay? Like a deep bruise or something like that. So first of all, we have blood vessels that rupture, okay, because of the injury. So it hits the blood vessel, causes it to open, causes an opening in the wall. So look on here. So at the site of the injury, you have this break in the wall of the blood vessel. And when that occurs, when that injury occurs, then endothelin is released, okay? Endothelin then actually causes constriction of the blood vessel and causes the muscles around it to like spasm, kind of close off so that it can limit the amount of blood loss. So that's what endothelin, the hormone endothelin, does. Now, at that point, you have collagen fibers that have been exposed underneath that endothelium, that inner lining of the blood vessel. So you got collagen fibers that are a lot rougher than that endothelium on the inside that actually will cause platelets to kind of adhere to it. So once those fibers are exposed because of the injury, it's gonna kind of attract platelets, if you will. But the blood vessel constricts so it can go on. Now the second step in that is platelet aggregation, and aggregation just means they're like clumping together. So platelets adhere to that particular area, so that area of where the injury was, and those collagen fibers kind of act as like a little net, like a sticky net. Platelets come in and adhere to it. Now when they do that, platelets actually release chemicals as well, so that more platelets will come in and gather up. Platelets kind of make like a little, they kind of just like plug up the wall, if you will. They like make a new little bed so that blood will stop escaping. Okay, the step 3 here. I'm sorry, forgot to read something. Platelet aggregation. Since platelets stick to these collagen fibers as well to the rough edges of the blood vessel wall, and they act like spackling, so they kind of fill in the gap there. Third thing that happens is you have a platelet plug formation. So when those platelets are attracted in, they all go to that area of the injury, and then they make it like a little plug. They kind of plug up that injured area. At this point, it releases what's a tissue factor, and which actually activates clotting factors. Now, the word factor, I know that's kind of a weird word, but you actually have 11 different clotting factors in your blood that have to react and occur so that your blood will clot and do what it needs to do. Now, if you guys have ever heard of the disease hemophilia, that is usually somebody with hemophilia or a hemophiliac is missing a clotting factor. There's several of them, could be any one of the clotting factors. So they're missing that factor, and that's what causes them to be like a free bleeder, if you will, or they would be at risk for bleeding even internally without knowing or whatever. We used to have kids come into the ER, and sometimes we'd have to give them factor. It's a very precise way that you have to administer factor. It's not just a medicine that you give one time and you're good to go. It has a special needle, special syringes, and special vials. I'm sorry. Okay, so a platelet plug occurs, clotting factors are released. And in light of that, let me read this part for you. It says tissue factor activates 11 different clotting factors or proteins in the blood. These clotting factors combine an enzyme called thrombin with the protein fibrinogen. Okay, so factors aid in connecting thrombin and fibrinogen. These two, this protein, this enzyme and protein, and whenever those two are combined, it creates fibrin. Okay, and fibrin is kind of like a stringy, it's like this fiber, if you will, that kind of wraps up around this platelet plug and acts as like a net, so that then at that point you've got blood cells that will come in and get kind of caught up in it. That will help it to heal and grow back to normal. So the fourth thing that happens is a blood clot formation. Okay, so it's easy for blood clots to stick to that fibrin because it's sticky. It looks like a net. They're just going to stick right to it. So that forms the blood clot. So red and white blood cells get trapped in the mesh. And then once that starts occurring, that actually releases a different kind of hormone, coagulation inhibitors, that then go back and cause the platelets to stop coming back and getting attached there. It causes a decrease in platelet aggregation. It also actually makes that little plug where the blood clot is, it starts to shrink. It's just like it pulls in and pulls in and pulls in until it kind of meets up that injured vessel wall again. So that's what happens. Every time you get a bruise, this is what's going on under your skin. Every time you scrape something and it starts bleeding, this is what's going on. It's pretty crazy, pretty cool process, but that's every time, bruise, whatever, that's what's going on. I think that is it. We're good to go. So you guys make sure you're working on your chapter packet. We will we'll go over blood typing while I'm here tomorrow. We'll go over blood typing, and then I'm going to let you guys Thursday at the end of class, hopefully we can get through blood typing pretty quickly. And then I'm going to let you guys, we'll do our blood typing test on each other Thursday. What I would really like for you guys to do for tomorrow is to read this chapter 10.2 or section 10.2. It is, I can tell you, I don't think it's very long. It is page 347 to 351. And two of those, all of those pages are only half a whole page. So it's not very long. Please read that tonight so that you guys will be ready. I want to get through the lecture really quickly Thursday, so that we can do the lab. I want you guys to do that. Friday, I got another lab for you guys to do. And I'm going to look at hemoglobin concentration. So this is kind of a fun chapter. It's got lots of labs. You guys are ready to poke yourself with a needle, but be careful to keep your hands washed. But I will see you guys tomorrow.